So, hello and welcome. This is now question 5. Okay. What I've drawn on the board here is obviously the diagram you get on the exam. Okay. We've got here a optical fibre. It's got the core, and obviously we've got cladding here, and this red ray here is meant to represent the light ray. It's got an instant angle of 60 degrees to the boundary, and it goes through the boundary. Now, the thing it should be alluding to straight away in your mind here is this angle is less than the critical angle. Okay. We'll also tell a few other things that the refractive index of the cladding, okay, which is the which bit I've shaded in, is 1.45, and the refractive index of the core is 1.55. Okay. So obviously that's a light ray, and it says calculate the critical angle of the core cladding boundary. So the core to cladding. Now that's really important because we need to know, well, what's N1 in terms of what's refractive index 1 and what's refractive index 2. Okay. Well, it says core cladding, so quite clearly it's already in the core, it's going into the cladding. Okay, so the critical angle. Now I think you're told that the critical angle in your formula sheet is sine of the critical is equal to N2 over N1. Okay. Now it will always be that way around because for total internal reflection to occur, it needs to be surrounded by a substance with a lower refractive index. So quite clearly, the second, because total internal reflection can occur at this boundary, but for it to occur, it needs to be surrounded by a substance with a lower refractive index, either N2 is bigger. So when we put it into this equation, okay, N2 needs to be bigger, smaller. And that would mean you're inverse signing a number less than 1, which is a thing for that as well. So if you do get it the wrong way around, you'll get an answer that's obviously bigger than 1, so you can't inverse sign that. Okay? So if you get math error, just try it the other way around. Okay? Right, anyway. So therefore, quite clearly, it's surrounded by the cladding. So the cladding is what we call N2, and the refractive index of the core is labelled as N1. So therefore it's just a case of inputting your values in. Okay, so it's 1.45 over 1.55. Okay, and that's the sine of the critical, so you inverse sine that, so you get theta critical is equal to the inverse sine of 1.45 over 1.55, which gives you an answer of 69.3 degrees. Okay. And that is your answer to A part 1. State why the light ray. I kind of already explained this just in my explanation of this diagram, but it says state why the light ray enters the cladding at Q. And it's only worth 1 mark. You need to state one thing, weirdly enough, and that's because the angle of incidence which is 60 degrees, is less than this angle of the angle of critical, which you worked out. Okay, so therefore it just refracts through the boundary. Okay, so that's all you need to say about this instant angle being less than the critical. Okay, so that's 6A part 2. I'll probably put it over here for you. So at theta, I'll put theta I, the instant angle, is less than the critical angle, theta critical. Okay, so that's all you need to say for A part 1, A part 2, see. A part 3 says calculate the angle of refraction at Q, okay, which is just angle here. It's very easy. Just using Snell's law. It's one of the easiest questions you will get in optics. Okay, so it's just simply N1 times sine of the incident angle is equal to N2 times sine the refracted angle. Okay, so there's just a case of inputting in what we already know. Okay, so we know obviously N1, as we said, that represents 1.55 times the sine of the instant angle, which we know is 60 degrees. Okay, is equal to N2, which is 1.45 times the sine of the refractive index. Now it's just a case of rearranging it. I wouldn't work out what 1.55 times the sine of 60 is just yet, although you can do. But it's all nice to keep it all together, so you're not accidentally copying something of an answer that it shouldn't be. Okay, so the sine of refractive index is just 1.55 times the sine of 60, okay, over 1.45, and then you sine inverse that to get the refractive angle. Okay, so the refractive angle is the sine inverse of 1.55 times the sine of 60, okay, over 1.45, and obviously you bracket it off. So therefore you get the refractive angle to be 67.78 degrees. Okay, and that would be your answer. 6b, now this one, as I said, is just listed answers, okay? There's a few on the actual mark scheme for this, so really it's one of them questions that I can just list the answers for. It says, explain why optical fibres used for communications need to have a cladding, okay? Now, this question is very common in optical fibre questions, okay? It's one of the ones that you always generally see associated with it, okay? And the main things that they look for is, one of the main reasons, what's definitely always on there, is about it because this optical core is obviously prone to scratch. It's made of glass, okay? So the cladding stops it scratching, okay? Which obviously could lead to the signals not getting to where they need to. And also having cladding makes the core very thin, okay? And you could talk about that. Another potential point you could mention, if you've got two optical fibres next to each other, because it's only surrounded by air, the light ray can just pass through and go into the next optical fibre. But whereas if it's got cladding involved, okay, it helps separate the optical fibres, all right, so they no multipath dispersion, okay. So there's a couple of points that I've listed there, and I've gone through them very quickly because, as I said, there's no real, it's just a knowledge question, okay? So please do check out, obviously there's the answers online and they're just listed, okay? There's no art to answering that question, it's just simply stating a point and explaining it, okay? That's the end of question 6 actually. It's quite a short question really. It's a very, very nice one, and hopefully wasn't too difficult. As I said, the only thing I might not have expected you to so the last two, so 6A part 2 and then that last part of 6B, okay, they were knowledge questions. The other two you could have just worked out from using the equations that were given on your formula sheet. So even if you had no idea about, if you totally forgot the theory to do with optical fibres, okay, you could have hopefully just done the calculation ones. And the other ones, as I said, were just simply knowledge questions. They were, the first one was just stating the fact that the incident angle was less than the critical, okay, and I have done a video on that, but just to recap that, when it's less than the critical, it refracts through, and when the incident angle is equal to the critical, it goes along the boundary. So if this was equal to the critical, okay, it just go along the boundary. Obviously that would be very good. And if it's greater than the critical, okay, it just totally internally reflects every time it was greater than the critical, okay, which it obviously just should be if it's totally internally reflective. Alright, so that's for that one. And then 6B is just a knowledge thing about, them not interfering with other optical cables. It prevents scratching, and it reduces the chance of multipath dispersion. Okay, so as I said, for 6B they're all listed online, so there's no real point in me trying to explain that. Okay, so thanks for watching. Hopefully question 6 was nice and easy for you, and we'll see you in question 7.